Hey, Calvin.
Hi, Dr. T.
How's it going, buddy? How's it
Good,
going?
good. How are you?
Excellent, excellent, excellent. So Abe emailed me uh, at 3 and said there's people in your lab. I presume that was maybe you and Pauline, or
No, no, it wasn't me.
hmm,
Today?
yeah, yeah.
That that's weird.
Oh wow. Are you in the
Well,
lab now, perchance, or no?
now I went there like last week, but not
Okay,
this week. Yeah.
okay. Oh well. Not like I can control it. So
hmm I have to. I'll check who. I wonder who's in the lab. That's weird. That's really weird.
yeah, that sure is. Oh well, no worries, no worries.
Oh, I think probably the people who like was at who sanitized the building because every afternoon they have to sanitize the whole thing.
Oh wow,
Yeah.
really?
Because one time they kicked me out to sanitize the building, but I told them like, can I yeah, I'm just gonna stay here.
Oh, no kidding. Oh,
hmm
all right.
So yeah,
That's
they
yeah,
always.
yeah, that's new. That's new. I didn't know
Oh,
that.
have you been to the lab lately?
I was there last week. I was there last week.
Okay. Do you only go there once a week or?
I you know, I'm kind of telling myself, oh, I'm gonna go this week or whatever, but so far I just haven't been coming in.
Oh yeah,
I
yeah. Because I was at the lab, but like every time I go there, because I go there like probably twice a week, and it's changing every time. I was like, is this Doctor T's doing this or?
hmm. Oh wow, well, I'm probably gonna go in tonight then.
Yeah, I was like, Dr. T, I was like, yeah, because last week it wasn't as met. I don't know what happened. It just like last week it was different. It looks different. I was like,
hmm,
what happened? I was like, what is happening here?
hmm.
So I was like,
Oh,
I'll probably Dr. T.
okay. Well, it's possible. I mean, it's possible that came in, but yeah,
Or probably
yeah,
the people
last,
who sanitize it.
yeah, possibly,
Possibly.
possibly. Yeah, well, let's see here. So, okay, let's see. Get busy here. Hello, Adam. How are you? Oh, Richard, you're at work.
Yep.
Hey,
At
Kun.
work.
Hi, Ivy. Hi, Dan. Hi, Adam. Hi, Carla. You're also at work. My goodness.
I'm on campus. My
Oh,
internet went down.
Oh, no kidding. Geez, things are going crazy. My son has a friend who lives in Medford, Oregon. She was just evacuated because there's a big old fire around Medford. Medford's just across the border into Oregon. It's 100, maybe 200,000 people or so, something like that. Sort of medium-sized town. It's crazy. All right. So, I am wanting to talk to everybody right now about the article, the Smiles article, I call it. It's entitled "Plug and Play Optical Materials from Fluorescent Dyes and Macrocycles." So, does anybody have any questions or comments or anything before I get sort of launch in here? Okie dokie. So I'll go ahead and start on this guy then. Can everybody see the article on their Zoom screen? Yep, good, excellent. Okay, so so dye aggregation is a common problem, right? And basically, it's related to the fact that dyes, when you concentrate them or crystallize them, tend to go dark. So that means that their absorption changes and their emission, more often than not, it red shifts. Sometimes it blue shifts, but but it tends to go dark. The intensity goes way down. And these authors figured out a way to use a macro cycle called cyanine. No. Well, it's a cyanide containing macrocycle polymer that will isolate the fluorophores from each other in such a way that you can take this co-crystallized material and add it to all kinds of different solutions and materials, and the dyes each retain their lambda max and their quantum efficiency, their intensity of their emissions. So the molecule that they bind it to is called a cyanostar, and it's called a macrocycle. It's I'll get you a structure on that guy. Right. Yeah. Here's a cyanostar. Right. And there's they might even have called it a cyanocrown, right? Because the it's a macrocycle, right? It's got about 4, 5, 6. Oh gosh, can't even count here. Like 1, 2, 3, 4, 5, 6, 7, 8, 9. 10, 11, 12, 13, 17, 18, 19, 20, 21, 22, 23, 24, 25, like 25 or 26 carbons, carbon bonds in the macrocyclic ring here. And so most of it is conjugated chicken fat, right, which is tert-butyl benzenes. This is a T-butyl group. It's very hydrophobic. That's a benzene. That's very hydrophobic. And then around the cycle, there's double bond, single bond, double bond, single bond, double bond, double bond, single bond, double bond, single bond, double bond, single bond, double bond, single bond, double bond. And so it's a conjugated macrocycle. But the thing that makes it work in this case is that there are 4 nitrile groups. And the nitrile group here is nitrogen bonded to carbon, and then that's bonded directly to this, I want to call it, keep wanting to call it backbone, but it's the cycle or the circular backbone of this cyanostar molecule. So what that means is that this highly polar molecule, cyanide, is projecting its negative electron density towards the center of this ring, right? So it has a certain amount of ability to stabilize cations, right? And so the dyes that these guys are using are exemplified by rhodamine, which is a cation. And when you make the aggregates of cyanostar, rhodamine, and the counteranion of perchlorate, they're referred to as the anionic complex here. And but the cationic dye molecule is somehow stabilized within this cyanostar interior, right? So let's see how this looks here, right? We've got these are rhodamines. These are perchlorates. This is the rhodamine cycle. There's the perchlorate counter anions. And I would not be surprised if there were, looks like, well, I think this is one perchlorate. This is a perchlorate anion. So this is, there's one perchlorate per rhodamine, and the macrocycles simply insert themselves around the anions there, and they separate the cationic dye molecules. And so this, so essentially what you have here is an anionic complex. So what you have to disregard what I said earlier. The dipole here is positive at this carbon, negative at the nitrogen. So what they can do is that these two complexes solvate the perchlorate anion with the cationic or with the positive charge density in the center of the ring. So, or the lack of negative charge density, however you want to look at that. So the victory lap here that these guys are taking in this paper has to do with a new type of material. And let's just see here. And the new type of material, for example, can be added to this is, it's not polylactic acid. It's a different kind of polymer that they made, that they printed this gyroid cube out of. But it just, it's an example of a condensed phase material that retains the emissive properties of rhodamine while in the solid state. I could be wrong. That the wavelength here looks significantly blue shifted relative to the rhodamine. This is, I'm used to seeing rhodamine, but I'm not exactly sure where they got this figure, whether this is a rhodamine dye in this case. But in any case, they can make, normally if you just take rhodamine 3B or 6G or whatever, they're all very similar. And you crystallize it, it will essentially make a non-fluorescent material. And however, if you co-crystallize it with these receptor molecules, then it makes a new material that is itself quite emissive. So what I'd like for you guys to do at this point is to understand how what the formation of the I think these are J aggregates or the H aggregates. Anyways, the aggregates that redshift the emission, how they form and how they look. So basically, if you have a fluorescent monomer, right, there's going to be some S0 and S1 state, and you'll pump the S1 state, and then it will emit, right? There's vibrational levels, associated vibrational levels here, which produce some Stokes shift that they're emitted in this diagram. And then when these materials aggregate, when you form the crystals, the dipole moments of the molecules interact such that ideally they can produce a splitting in the excited state, which will then tend to redshift in this case, and also quench the emission. So, and that can be understood from two perspectives. One from the perspective of excitons, and two from the perspective of the aggregation of the excited states. So hold on here. So let's first talk a little bit about excitons. Okay? So excitons have this quality that their coupling constant, or this is actually, this is not directly from excitonic theory. This is from aggregation theory, right? Where the aggregated molecules, so you could take a pair of them, and their coupling, their optical coupling constant, J, will be proportional to their dipole moments, and then 1 minus 3 cos squared theta for the angle between them, right? And then there's a 4 pi epsilon in the denominator and an r cubed, where r is sort of the center distance between the dipoles. And cos squared theta is the angle between the dipoles, and then u is the dipole moment. So this guy here, you might ask yourself, well, what does this look like? Right? And what this looks like is this function here. So this is the 1 minus cosine squared theta part of it. So cosine squared theta, it simply never goes negative, right? and then 1 minus the cosine squared theta will oscillate between 1 and 0 on these 90-degree intervals, right? So between 0 and 90 degrees, you go from 0 coupling to maximal coupling. So and honestly, I don't completely understand this, but that is what the formula says, right? I would actually think that minimal coupling might happen at 90 degrees here, but it could be the way that they're defining theta, the angle between the transition dipole moments. And these mu values are the transition dipole moments. So recall that the transition dipole moment comes from the angle between the center of mass of the, the transition dipole moment is a vector between the center of mass in the ground state and the center of mass in the excited state. The center of, not mass, but center of charge in the ground state versus the center of charge in the excited state. So in any case, when this angle is 0, there's minimal coupling, and when it's maximal, then 1 minus 3 cosine squared theta. That is actually going to, look different. Hold on, let me make this change. Oops. Let's look at this 3 times. Okay. Aha! So this does have maximal interaction at 0. I messed myself up here. And so here's the total function. This is 1 minus 3 cos squared theta. Just see if that's correct. Yeah, 1 minus 3 cos squared theta. Okay. So here is the function that this guy's going to have. So it'll change between a bathychromic type shift and a hypsochromic type shift as you go from, as the angle changes from 0 degrees to 90 degrees. Interesting. So, so this equation predicts the entire range of shift values that can happen for a given angle between the transition dipole moments of the molecules. So these things are all kind of abstract, right? But the thing that we can extract from it is that there's this angle dependence, which is fixed to the molecular geometry, right? So if the molecules sit there and if they're stacked in a crystal, like such that they're in a lattice where one molecule is oriented like this, the other is oriented like that, then this will fix that theta value probably at 90 degrees. And then on the other hand, if they're completely parallel, then that theta value will probably be 0 degrees. And then in reality, they'll probably be canted somewhere in between those two angles, right? But what this formula applies to the solid state, right? We're applying it to the solid state here, so the theta value is not going to fluctuate. So the other thing to recall here is that there's an oscillation in theta, and then there's an r cubed dependence, right? So the r cubed is essentially the distance between the molecules, right? So that means that the effect drops off very quickly as the radius increases, right? So mu is coulometers and R is meters. So we've got coulomb squared, meters squared, and then meters cubed. So this all has a 1 over R unit to it. So, weird. Anyway, let's see here. So, oops. That's actually where I want to be. So, the J value is this coupling term here. So the magnitude of the splitting that the, can you all see this okay? The magnitude of the splitting value here is what's determined by R and theta, right? R, theta, and mu. The mu values are going to be large for all these dyes because the dyes are themselves good fluorophores, right? But the, so that we can say, okay, that's going to be large, right? And so the only thing controlling this splitting is R and theta. Right? Theta is set by the crystal structure, and R is also set by the crystal structure. Right? So we can see here that the coupling constant at half a nanometer and at 1.5 nanometers here, it really, really drops off. So so this could be, this is 3.5 or 0.35 nanometers. This is probably the contact distance for pi stack dyes, right? And then 5 nanometers and 50 nanometers. So if you can get them, I'm sorry, 0.35, 0.5, and 1.5 nanometers. If you can separate them by 1.5 nanometers or 14 angstroms here, then you can essentially wipe out all of the coupling that normally occurs in these dyes. So basically what they're saying is that in the SMILES crystals, they are held apart at approximately 1.5 nanometers, 14 angstroms. An angstrom is roughly the size of a helium atom. So a carbon-carbon bond might be a couple of angstroms. And so this is maybe 10, somewhere between 10 and 20 carbon-carbon bonds in the distance between the centers of the molecules, or whatever this R actually refers to. Does that make sense? Can you see yourselves? This is how you all look. I think it's lovely. So Dan is always in a dark cloud, and Aditya's he's halfway in the light. Kenny is in the light, but it's in a strange wonderland from an anime. And then you're at a daycare, right, Ivy? Are you at work somewhere?
This is my own bedroom.
Oh my goodness. That you have a sign. It says, "Can I do?"
Oh, it's a lyric from a song.
Oh my God, that's so cool. You're like a teenager. I love it. Kai is in space. Ikun is in the same place he always is, and all I can ever see is the ceiling. And Calvin he's sort of in a strange Star Wars thing, because he's warping in and out of existence, you know. And behind him is a periodic table, as usual. I should get a cool background. I don't know. I'm too lazy. And let's see. Richard's at work. He works in a cubicle. Actually,
This is my room.
That's your room?
No.
Oh, God, you got me there. I was thinking, poor kids in an institution. Oh, my gosh. This is Adam's room? Was it like a dorm room or an apartment room? Yeah. Okay. So I'm not really sure what more to even talk about, like in terms of this stupid smiles paper, because it was really interesting when I first looked at it, but I'm so bored with it now. So, we could, but I want you to at least understand what I've said about things so far. It's like, BFD, these guys broke the coupling between fluorophores and crystal. They made really bright crystals, Apparently the crystals are super bright, which is awesome, I imagine that, if you actually dissolve them in solution, then, you got to be careful to recrystallize them so that they come back in this interesting packing, But apparently they can just shovel this stuff into the resin for their 3D printer and create these stupid models. That's a PMMA, or it's a methacrylate based 3D printing solution. Have any of you ever had a 3D printer?
I've seen 3D printed things and seen a 3D printer.
Yeah.
We have one at work.
Yeah.
My friend has one.
Yeah. I actually have one, but I got sort of frustrated with it because I tried to make this big old key holder thing, and what happened was it'll make small little flat things just fine, but it's really slow. And if I try to make larger things, for some reason it uses this PLA wire, this wire stuff. It squirts it through this nozzle, this heated nozzle. It melts it and it moves the nozzle around, and it'll start making spaghetti, and it won't be connected as it goes up, So the first 10 layers will be fine, but then it'll be after that. So I actually made this stupid 3D printer. I bought a kit, but I made my own 3D printer. And it really broke my heart because my son was in freshman in high school and he was helping me make it. We had this project together, right? And before it was done, he lost interest. Never came back, right? So then it was just my toy, right? I had him. But then I lost him, and so it was my toy for a while. I made a few things, but then I couldn't make anything else because it was just like spaghetti. However, about a year ago, I put $1,000 or $750 something into SnapMaker. It was this Kickstarter project. Have you guys ever seen a SnapMaker? They look really cool, but oh my God, it's been forever. They still haven't delivered it. They said they're going to deliver it in between August and October. And I'm just dying to get this stupid thing because it'll make 3D prints, and it'll also do CNC routing, so you can put a little extruder on it and it can make 3D prints. You can put a little motor on it with a little cutting bit and it can cut things out, right? Or you can put a little blue laser on there and it can etch things, you know. So it really pushed all the stupid, you know, stupid maker buttons on me, you know. I don't know that I'm a maker, but it's like the mental, I think of myself as a maker, you know. So anyway, but yeah, I'll let you know how that goes. But basically, these are nice. These are really bright. These are bright materials. However, because they're, you know, because they are co-crystallized like this, right? I suspect that you can screw them up pretty easily, right? Because if you like, because we could just look at this, the way that they make it, you know, is you take your dye solution, you add the receptor, and then you just fucking precipitate it. Sorry, excuse my language there, right? And then you've got a material, you've got these, you know, these co-crystals that are emissive, right? And in this case, they added them to polymer resin, right? But I'm guessing that there was some dissociation of these nice co-crystals, right? So when that happens, one of two things can occur, right? One is that the molecules, the Smiles crystals, can revert to monomers, right? Which is not really that big of a deal because they'll retain their emissiveness if the polymer doesn't tweak them too much, right? Or they can retain their packing in the Smiles crystal, right? So now there is something I'd like to tell you about dyes in plastics, right? Here they're just advertising, right? But let's look at this, right? There's absorption and emission, right? Absorption is a little bit like excitation, spectroscopy, excitation, right? And you can see that there's this typical rising, there's a sort of a soft wall and a hard wall. Right? The black is the monomer and the blue is the Smiles. Sorry. Let's read the caption before I go. This is CDENF. So these are rhodamine 3B perchlorates. The black lines are in solution, right? And the black lines are reproduced down here, right? The blue is for solids made from, it's from like solid rhodamine 3B, and this is the fluorescence of solid rhodamine 3B, right? And if you add the cyanostar, then they look like this. Yeah? So this is kind of cool, right? And then here's a solid film, and then if you add the cyanostars, the emission comes up maybe 20 or so, which is, it's a cool thing, you know. However, I wanted to tell you something about the optical spectra of dyes in plastics. Okay. So I'm going to have to dig that out. It's going to take me just a second. Yeah, so whatever. There's a whole bunch of different, these cationic dyes, cyanine dyes, there's a pyridine dye, there's an oxazine dye. They're all cation. And basically, it looks like the cyanostars basically coordinate the anions. Right? So, really interesting. So here's the different colors they can make, etc. You guys stare at the colors. I'm going to find a paper in my Chem 250 archives. It's going to talk about this. Those notes. Yeah, there we go. Vanderboot. There we go. Well, this. Oh yeah, this is it. This is it. Yes. Okay. This is actually better than the one I thought I was going to get because there was one where some of the conclusions were, I think it was actually retracted. I was like, oh shoot, am I going to show them a retracted science article? It's so weird too because in the 2000 to 2006 period, I reviewed two science articles. These articles in the journal Science, right? And well, I reviewed a whole bunch of articles, right? But two of them were retracted, and one of them I didn't see it coming, but the other one, I was in class and we were talking about this isn't right. Something's not right about this article, and it was kind of interesting. That was I'll tell you the story later, but so if you take small molecules, and here they're going to use rhodamine 6G. And you've seen this whole stupid thing. There's the fluorescent transitions, blah blah blah. And you can you can dissolve the monomers into you can dissolve the dye into polymethyl methacrylate. And polymethyl methacrylate's it's what is that? I think it's the dye they use in plastic windows, but it's a clear plastic plastic, and you can dose this with low concentrations of the you can dose this with low concentrations of the rhodamine, right? Of rhodamine or whatever, right? And you can, it's actually or oxazine in this case, right? And you can you can easily dilute the dye down to a concentration that in any given, say, 5 by 5 micron patch, there might only be 20 molecules, right? So in this case, here's these 20 molecules that are setting near the surface of this PMMA. And what they've done is they've got a laser, they've got some sort of laser excitation emission, right? And here's a fairly common way to do this, right? Because you can take a microscope objective with a fairly large lens at the end, right? This is what's referred to as a high numerical aperture lens, right? And you put you shine a laser in right near the middle here, right? And there's a couple lenses, and this narrow collimated beam focuses right down there. And then radiation that's re-emitted from this spot is emitted over a wide range of angles. You can pick it up using the same lens and then collect that emitted radiation along the same optical axis that you're excited, right? So it's like use one lens and you put a laser down, and then you use that same lens to collect. It's used a lot in Raman as well, this sort of technique, right? And you've got to filter out the laser light somehow, spectrally, something like that, because these are not bright spots, but they're definitely there. Right? And then you have a translating stage, most likely, and you scan around this a bunch of times, and you can see here, you make a false color plot, and the high count rates at given points are due to the presence in this near surface region of a single oxazine molecule. For example, you make a really thin film or something, you just have very dilute oxazine, and then you can space out these molecules so you can see them one by one, right? So this single molecule approach to seeing the spectra of the fluorescent spectra of molecules is pretty cool, I think. And it brings us back to the first day when I was talking about there's, any spectrum you see of a molecule is an ensemble average over time and solvation and configuration and many, many molecules. Except in this case, you can look at a single molecule, right? Because it's in a solid, you can look over a single solvation state, right? You're still averaging the bejesus out of time, but you can make sure that the time is the observation time may be shorter than, say, a tumbling time of these molecules in a material like PMMA, right? PMMA has a glass transition temperature that is above room temperature significantly. Maybe it's 80 or 90 degrees, depending on the molecular weight, right? So if you do this down at 25 degrees, you're essentially in a really solid phase of the PMMA, and the molecules won't, even the dye molecules that are trapped in the PMMA, they won't be flipping around and tumbling on the time scale of the measurement, right? So the idea here is that if you have a laser coming in here, you can see this spot. So let's just think about this for a second, and I'll try to. They may talk about it here, so let me go down. So I turn on this stupid this stupid scanner thing, this webcam, and my laptop starts to crash. Maybe it's something to focus on here. Some pretty crappy software. There we go. So you've got this molecule, right? It's M. It's in the focus of a laser, right? We've got plenty of excitation light coming down here, right? But we have to collect fluorescent photons faster than the dark counts in the detector. Right? So what does this tell you about the lifetime of the fluorophore? So that lifetime, well, yeah, I said everything I need to say. Dan is in a cave now. He's in a real cave now.
Does it have a small lifetime?
Yes, it does. It has. You don't usually say small. You say short. Right? It has a very short lifetime. Exactly. So tau fluorescence is very. So it's typically less than 1 nanosecond. Right? So.
Hey, you have the videos up.
Yeah. Sorry. I like seeing you guys though. I'm going to put you down on my other screen. I put you next to my webcam so that when I talk to you, it looks like I'm looking at you. But you never know what I'm looking at. So anyway, the fluorescence's lifetime is less than 1 nanosecond. So that if the tau for fluorescence is less than 1 nanosecond, about how many? Mom. No. There's something I want you to see. Here. No, you want them to see you. She's been shopping. She's been to Macy's. It's very, very uncharacteristic of her. So I want to see what she bought. I'm showing everybody what you bought, honey. He's always after me. Trying to get to work, trying to get me to work. Okay, so so about how many fluorescent photons per second can we collect? Maximum. How would we do that calculation? So obviously, we can start with a weak laser. And if we have a weak laser, we'll have weak fluorescence, right? Okay. Then we're going to crank up this laser. And so the laser power and then the fluorescence, right? There's going to be a point here, right? And as we crank up the laser power, it's got to crank up linearly, right? But where does this stop? Where does that stop being linear? Okay. The fluorescence is going to be, let's change the units here to photons per second. And let's say that we're dealing with a tau value of 1 nanosecond. Okay. We've got the fluorescence here is because the little beastie, and let's say that we can collect over every single photon that it emits, right? And it's a perfect emitter. The quantum efficiency is 1. We got great geometry. We got 1, 2, 3, 4, 5, 6, 7, 8. So let's say that this is 100 million. 2, 3, 4, 5, 6, 7, 8. And we've got this thing is linear up to 300 million photons per second. And we expect it to continue going up. Okay, so I just posed a yes or no question. So you know your chances are around 20%.
I'm gonna say no.
Ah, she's bucking the trend. She said no, right? So now I'm going to cut you down to about 10%. I'm going to give you 3 options. Actually, it's still 20. I'm going to pretend it's. There's this, this, and this. A, B, or C, right? Which of those 3 actually is observed, the observed fluorescence versus laser power? And so this is a single molecule emitter, right? Okay, so are you guys putting this in chat or are you consulting me over chat again? Okay. Adam said C question mark. Okay, Adam, since you're so smart, why don't you tell us why you think C question mark? I didn't hear anything. I think he unmuted. I didn't hear anything. It's okay, I hear you. I hear you. I hear you. Beep, beep. Remuted. Okay, you can write it in chat. Yeah, you got a new headset. Sorry, I guess he left out the D. That's really racist. Sorry. So, mic not working. Okay, so I will type then. Y, C. Oh, really? Okay, so
Wouldn't you just end up like photo bleaching your molecule at some point? Like, isn't there just kind of like a plateau of like where it can't
okay.
fluoresce anymore?
So if it when and if it photo bleaches, the amount of radiation goes from say 100 million photons per second to what? 0. Right? It's dead. So I'm presuming here that we can do this entire experiment without photo bleaching. Right? Now, it's going to photo bleach, but if it doesn't, and we're able to get away with this, is it going to become super luminous, continue linearly, or become subluminous? I don't know. Recall what we were just talking about there. Lifetime's about 1 nanosecond, right?
Yeah, so wouldn't it stop fluorescing after the time that it has, after its lifetime? So it would it stay
Yes.
linear then, since
So it's going.
yeah, so linear. I'm gonna
Right.
go with
This is linear. This is linear, right? Because it only spends 1 nanosecond out here, right? How long is 1 nanosecond? That's 10 to the minus 9 seconds, right? That's 1 billion. That's one. That's 1,000. That's 1,000,000. That's 1,000,000,000. You know. Oops. Oh shit. I'm missing some zeros here. No. Sorry. Oops. It's probably actually more realistic than when it's 1,000. So if we got 100 million photons per second, right? If every time we create a ground state, it immediately pumps back up. It spends 10 to the minus 9 seconds here, then emits. Right? And what's the maximum number of photons per second that we can get out of this?
Wouldn't it just be one?
1 photon per second?
Wait, can you repeat that again? So you said it's
Sure. Yeah. So if as soon as we form a ground state, instant we form a ground state, a photon is absorbed and creates an excited state.
Mm-hmm.
And that excited state lasts for 1 nanosecond. Then it re-emits, and we get a photon out, right? We're counting these photons that come out. How many photons per second can we get? Maximum?
Oh, the 10 to the 9.
Ding, 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 ding. Thank you so much, Kenya.
Oh,
You get 10 to the 9. So basically, as the laser power increases, this is going to do A, B, or C.
It's gonna do 8.
It's going to do A. The fluorescence is going to increase. It's going to increase.
I'm so confused now.
Okay. So this is like if we get to 10 here, this is 10 to the 9th photons per second, right? Out here, right? So this is the absolute maximum that you can create with this molecule, right? You cannot, even if you instantly, like even if you input so many photons that the lifetime of the ground state is 0, you know? If the lifetime in the ground state is 0, you're still only going to be producing 10 to the 9th photons per second, right? So you're basically just cycling. As soon as it fluoresces, you immediately excite it. But after you excite it, it takes a nanosecond to relax. Then you excite it immediately. Another nanosecond, relax. Excite it immediately, it waits a nanosecond, relaxes. Excite it immediately, waits a nanosecond, relaxes, right? That's what you were telling me earlier, right? Yes.
So then wouldn't that just be a line like that? Like straight?
It would be horizontal. Well, would it be a vertical line or a horizontal line or a straight line up like that? A, B, or C? Because obviously, if you have this is the laser power, you know. This is the excitation power. And then this is going to keep going up, 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 up. And then as we start getting around this threshold of 10 to the minus or 10 to the minus 9 seconds, you know, when we're getting, 300 million, 400 million photons per second out, right? The question is the emission rate going to increase, or is it going to keep going straight, or is it going to flatten out?
It's gonna keep going straight because it's not changing.
Okay, so that means that if we put, let's make the same scale here. We've got, and this is like 500 million photons per second here, right? And then we go to 1 billion photons per second here, and we go to 2 billion. If we put 2 billion photons in per second, can it create 2 billion fluorescent photons if the excited state is 1 nanosecond?
It would just eventually turn into C, right?
Who said?
Me, Aditya.
Oh, hi Aditya. How's it going? You're lost in a dark cave.
Indeed.
Yes. So Aditya says it eventually is going to turn into C. So why is that the case?
So, like you said, we can only get to that threshold of 10 to the 9 photons, and we can't go past it because that's the amount of time it takes to, I guess, fill. So once we get the laser power to 10 to the 9th, I think I phrased this wrong, but once we get to 10 to the 9th, the detector won't be able to detect anymore. So even if we increase the laser power, it's going to stay at 10 to the 9th photons per second, I think.
Okay, so let's say we had a perfect detector, and the detector can detect a gazillion per second. Right? It's sort of like, oh yeah, so Richard says 10 to the minus 14 seconds to absorb. Yeah, let's say it takes 10 to the minus 14 seconds, right? That's nothing compared to that. That's 100,000 times shorter than 1 nanosecond, right? And I don't know where they get that number, honestly. I think that's a bunch of hooey, but I could be wrong. Yes, babe. It ends as soon as I have a good video for you. Ah, It's a. Oh no, but it's playing in the sand. It's something that plays in the sand. She doesn't know it's till 7:15. I'm gonna get her to come.
Try though.
Yeah. So, so Dan, what's the answer
The didn't we already get the answer? What was the question?
here?
Yeah, isn't it tails off at 10 to the ninth because what happens if a perfect detector? The speed of the fluorescence, it's the same, it's I don't know, it maxes out, so you can't get any more photons out.
Right?
I'm not sure how else to describe it than that.
Yeah. So you don't have to describe it any better than that. You just have to get somebody else to believe you. So try to explain it to Kenya so that she believes you, because she will not, no matter how hard I try, she will never believe you.
Well, I can think only of like a rate of a reaction instead. So if it's a reaction that goes at 10 to the ninth or 10 to the negative, I guess 10 to the negative ninth, right? Then it will max out eventually. And even if you add more light and more heat and everything, it's not going to get over that pass because the speed of the actual reaction is, you've already gotten to it, I suppose. That's all I got.
What do you think, Kenya?
I'm you know what? I'm good. I understand.
You understand? What's the answer?
It's C, Dr. Terrell.
It's C, okay. But you can't say why. Is that true? Or you're like, you understand, but you don't have a way to articulate it. Is that true?
Me?
Because Dan can sort of articulate it based on this kinetics metaphor, which is, it's okay.
Well, it's basically, you can increase the power of your, what is that? The
Your radiation, your light,
right, of the
your
radiation,
excitation.
but you've already reached the maximum of the photons you can release, right?
Right. Because there's only one, within our world right now, we're not considering stimulated emission, right? But within our current theoretical world, there's only one mechanism by which it can emit, and that's by being excited up into the vibrational manifold, relaxing down, waiting for a nanosecond, and then emitting. Excited, waiting for a nanosecond, then emitting. Right? So if we had a similar dye, yeah, I mean, it's still 7:15. She thinks I'm torturing you guys. She has no idea. I try, but I tend to lose you. Okay, so the answer here is C. The answer is C, because we can only cycle so many states out of this molecule, right?
Dr. Terrell?
Yes.
So I was a little bit confused. Are we asking? Are you asking what the behavior is going to be like approaching 1 billion, or?
Yeah.
Oh.
Yeah.
So before 1 billion, it's not going to go linear, hit a billion, and then flatten out.
Yeah, I mean, you could say that like it's going to plateau at some laser power, right? And that's really all I'm asking, whether it does something weird and shoots up, like it becomes super luminous, or it just stays linear, or whether it limits. The fluorescent output stops increasing with increased laser power, with increased irradiation.
So is the y-axis 1 billion then? Is that what?
Yeah. So this is 100 million on this first little tick mark thing. It goes 2, 3, 4, 5, 6, 7, 8, 9, 10. The billion's probably right up around here, right? And I just said it's plateauing somewhere down there because, there's other time scales to consider. I don't know. I'm just making this up. Give me a break, man. Okay, Carla, does this make sense? So, Kai? Makes sense? No? Equin, makes sense? No?
I have a quick question.
Yeah.
So, is there like until a point where the graph is linear and then it curves, or is it just a curve from the beginning?
It's essentially linear at the lower radiation.
Oh, okay.
I mean, it's always a curve, really, but it's linear and then it curves.
Okay.
So.
Thank you.
Okay, so we have very, okay. Yeah, so what about comparing to solution saturation? So basically all we're saying here is that we have this stupid molecule trapped in a laser focus. And we're looking at the rate at which it's emitting photons, right? And we're just turning up the intensity of the laser, the radiation. And that guy is just emitting, oops, sorry. The guy's just emitting light. So, kinetics comparison, yeah. Well, I mean, kinetics tend to do the same thing. They do tend to limit, right? Because there's when you increase concentrations of reactants, then there comes a point in time where it takes a certain amount of time for things to diffuse, come together. But that's a little bit of a messy subject. I don't really know that much about it. Okay, so now let's say so in order to do this experiment, right, with the single molecules, we need a short lifetime fluorophore. We need a good strong laser, right? And you can see here, that with this was 1999, so I know you guys weren't born, but to me it seems like fairly new. But there was a total of about 100 counts per second. This is on a charge coupled device array. Or actually, I don't know. Could be a photomultiplier, because they were probably scanning the substrate, right? And so, but it's a maxed out, really sensitive detector. The background subtracted it down to 0. And these guys are well above the noise level, but still around 100 counts per however long it takes them to integrate this. It could be maybe 100 milliseconds, even as short as 10 milliseconds here. But the point is that this is a single molecule, right? Each of these blobs is a single molecule. So you know how we spend a lot of time emphasizing how fucking small a single molecule is. Well, they're still fucking small, but you can see them if you've got a good fluorophore that can generate a lot of photons per second. You've got good collection optics, you've got a strong laser, and you can immobilize it, But then once you do this, Then you've got an interesting sort of a platform where you can look at what's called spectral wandering. And this is not a great example of it, but I'll go ahead and make it a little bit larger for you to see. This is actually just the frequency of the laser, and they scan the laser frequency up and down, right? And then they do this over and over, and they look at the fluorescence. Right? So this is an excitation scan, essentially. And the emission wavelength is changing at every point in time. Isn't that crazy? So this is scan 1, 2, 3, 4, 5. And what this means is that for this individual molecule, and on this time scale, it's changing position in the laser such that it takes a slightly different frequency to excite it. Or such that takes a different frequency to excite it. So this is called spectral wandering, and it can only be observed for individual or single molecules. Okay, that is enough for today. I have overslept, I've overstayed my welcome. I just want to emphasize one little thingy, which is that there is an assignment to do, right? And it's called Questions for Smiles paper. It is due on the 17th, which is a week from Thursday. Okay, guys? So do that, turn it in, and we will, and if you have any questions, harass me by email, office hours, or in class, and I'll make sure and record your questions and answers, and we can get these things. All righty? Okay, really is. Thank you, guys.
Hold on, wait.
No, yes.
Does this Miles paper talk about the J aggregation and the H one? Because I tried looking at it on the other paper, the chapter 6 scoop thingy.
I know it's pretty opaque, huh? It's pretty opaque. You know, I used to have this real simple picture of J and H coupling, and I'll try and put together a clear picture for you, but suffice it to say that there's just, when you aggregate dyes, they quench, and they either blue shift or they red shift in their emission.
Okay.
So in one case, their emission could be a little bit higher energy, or could be a little bit lower energy. You know, so that's about it. You know, you don't need to know the details of how that happens, except possibly this cosine squared theta thing. But that's in simple parameter space, right? That's in terms of radius and angle.
Okay.
All righty. Good. Excellent. I will see you guys on Thursday.
Okay. Bye.
Okay. Thanks.
Thank you.
Thanks, Dr. T.
Night, Dr. Tao.
Thank you.